Hello everyone. Welcome to my class. I'm Khalid. Today I'm going to go on a journey to explore the collision and the conservation of momentum and energy. Are you ready?
Yes.
So let's take on our journey. When we see the fireworks light up in the sky, we will see it's very beautiful, splendid, and it is also a nice display of momentum and energy. And so what do you see in this picture? Try to describe it in adjective or nouns. Any volunteers? Frameworks. Fireworks. Yes, is it fireworks? Okay, nice.
Looks like star shining.
Yeah, looks like star shining. Exactly.
Lots of colors.
A lot of color. It's colorful, right?
Yeah, colorful.
Great.
Lots of
It's if you and you
different ways of fireworks.
different ways of direction. They are kinds of trajectory, right?
Yes.
Right. Okay. Great. So at a microscopic level of fireworks, we see a lot of patterns and shapes, and also they have kinds of trajectory that is trails and colorful light, right? But if we take a closer look, we have to figure out the internal mechanism. So we also wonder, how does it work? How does it work? If we try to explain it, we have a small review. What are the momentum and energy? Momentum is just like equal mass times velocity, and momentum is a vector, so it has a direction. Okay, and another one is the energy. Energy, there are kinds of energy in the world, such as kinetic energy, and the potential energy, and so on. So what's the conservation of momentum and energy? Is that if the center of the mass didn't move, the momentum is conserved. And the other one is, if we count all this energy, just like kinetic energy and potential energy and the thermal energy, and the all energy comes into one, that will be conserved at the end. Okay. So the fireworks in the world must obey these two principles. So let's take a closer look at the mechanisms in fireworks. We can generalize these phenomena into a two-particle system. So the two particles collide with each other at first. So the collision occurs. And second, the center of the mass did not move horizontally. It just flew into the sky and did not move from left or right. Okay, so the momentum is conserved horizontally. Okay. In the end, the chemical energy will transform into kinetic energy, so the energy is conserved. Okay. So what else can we see these principles in real world? Now I will try to do an activity, because actions speak louder than words. So I will pair you up. So two people in a team. Okay. And try to have a more space, large space, because we will do an experiment.
Large space. Large space. How large?
So should we stand or sit?
Sit on your chair. Sit on your chair.
Sit on the chair. Sit.
But move have more space. Okay. Right. Okay. Ready?
Ready.
So we want to push each other. Just see. And try to push each other and see what happens. You see what happens. Okay. So have you all practiced?
Yes.
Okay. Yes. Okay. Thank you. And see the videos.没有错。And if we see a video, you will like video is two people will apart at the end. So the one vector is P1. So the momentum the people Jamie has a momentum P1 and Morphy has the momentum P2. And they are opposite direction. So P1 may equal to 1 kg times m and divided by s. And P2 is minus 1. If we plus these two into 1, and we will get 0 at the end. Right. Okay. Okay. So let's take a closer look and to sum up some knowledge. So what is the change of the momentum? Because the center of mass did not move, so the momentum is conserved. And where does the energy go? Murphy, how do you feel in this experiment?
Pushing hard, I feel tired.
You feel tired, right? So where does the energy go?
She observed. Absorbed.
So your internal energy is transformed into kinetic energy, right? Oh, so the energy is conserved. Right. Okay. 好像按到了。
对，你要选那里。
Okay. So we do want take a closer look at the collision process. I will play on a video. Okay. So we'll see a poor koala just someone hitting on his face, right? So what did you see in the koala's face? Tell me about it. Twisted. Great. You have a king observation. Right. Okay. So another else. Suffer. I think it's flattened nose. Right. Okay. So if we take a closer look, it just twisted, flattened, and under pressure. So the procedure is the first one is the face approach to the koala face, right? Just like this. And the collision occurs, right? And third, the kinetic energy converted to potential energy, right? Just like this. Flattened nose, you know? And the potential energy also converted to kinetic energy, reversely, right? Just like this. And flattened nose is restored. But the koala is flew away. Okay. So at the end, the two objects is apart. So the fireworks and we are do those two experiments also obey these two conservation laws. That is momentum conservation and the energy is conserved. So I also want to wonder, where does it go? Where does it go? Where does koala go? And how much fast it will go. So if we want to predict the motion of particles or the object, we also do the experimentation, and we want to have some calculation of the speed. So we need to derive the formula and predict at the end. So next class, Jamie will tell you how to figure it out, this problem. So thank you, everybody.
Feedback, please. Any feedback?
Multimodality.
Lots of multimodality, yes. Very good. Anyone else? Yes.
I love the practice. We push
Each other.
each other,
Yes.
and then the koala
Yes.
comes and we can use an interesting way to attract our motivation to want to learn more.
Yes. Good, very good. Excellent. Any other feedback? So I thought it was very well prepared. You had stepped out all of your lesson, which was really good. And a very interesting topic, actually, using fireworks and motion and movement and energy. I also liked the examples that you did. I like the koala one, but maybe you could have got them to observe, like themselves, or even take images themselves. Or you could have shown them the example like you did, and then get them to do their own. So just some more activity. So, but it was good. Yeah, overall, I think that it was very sophisticated and thoughtful in your lesson plan. So well done. Congratulations. So everybody, now I'm going to